Welcome to Chapter 3 of the Autonomous Driving series. In this chapter, we shift from the technology foundations we covered earlier to the real-world commercial deployments and cutting-edge AI techniques driving the industry forward. We'll explore how robotaxis are already serving hundreds of thousands of rides per week, how autonomous trucks are reshaping logistics, and how breakthrough AI approaches like end-to-end learning, world models, and generative AI are pushing the boundaries of what autonomous vehicles can achieve. The robotaxi industry has reached an inflection point. Waymo One, the autonomous ride-hailing service that grew out of Google's self-driving car project, now runs paid driverless rides across several U.S. metro areas, including Phoenix and San Francisco. In China, Baidu's Apollo Go operates a comparably large service across many cities, and the two together account for the great majority of driverless rides worldwide. Tesla has launched a pilot robotaxi service, aiming to leverage its large real-world driving dataset. Meanwhile, Zoox, owned by Amazon, has developed a purpose-built vehicle with no steering wheel, designed from the ground up for autonomous operation. Pony AI completed a U.S. listing, becoming one of the first pure-play autonomous driving companies to go public. Autonomous trucking tackles one of the most practical use cases for self-driving technology: long-haul freight. Aurora Driver operates autonomous trucks on the Dallas to Houston corridor, one of the busiest freight routes in the United States. Kodiak focuses on a hub-to-hub model where autonomous trucks handle highway segments between transfer hubs, with human drivers completing the first and last mile. Plus has taken a unique dual-mode approach, offering trucks that can switch between autonomous and human-driven operation. On the delivery side, Nuro introduced its third-generation R3 vehicle purpose-built for last-mile delivery. Amazon developed its Scout sidewalk delivery robot, but later wound the program down. Its separate acquisition of Zoox targets the robotaxi market rather than last-mile delivery, so Amazon's autonomy investment now sits mainly on the passenger side. End-to-end driving represents a paradigm shift in autonomous vehicle architecture. Instead of separate modules for perception, planning, and control, a single neural network learns to map directly from camera inputs to vehicle controls. Recent versions of Tesla's FSD exemplify this approach, using a single neural network that takes camera images and outputs steering, acceleration, and braking commands. This dramatically simplifies the software stack and allows the system to learn behaviors that are difficult to program explicitly. Supplier platforms from NVIDIA and others bring comparable end-to-end capability to the broader industry, providing frameworks that automakers can adopt rather than build in-house. Wave's Lingo 2 adds an interesting twist by conditioning the driving model on natural language instructions, allowing the vehicle to understand and follow verbal commands like, "Take the next left turn." World models represent a fascinating approach where the autonomous vehicle builds an internal model of how the driving environment works and uses it to predict future states. Think of it as the vehicle imagining what will happen next before it actually happens. NVIDIA Cosmos is a foundation world model trained on massive driving datasets that can generate realistic future driving scenarios. Wave's Gaia World Model series specializes in generating photorealistic driving scene videos, useful for both training and simulation. The Drive Dreamer series explores how these generative models can synthesize diverse driving scenarios. Awkworld takes the concept into 3 dimensions, building a 3D occupancy-based world model that predicts how the volumetric structure of the environment will evolve over time. These models are becoming essential for safe planning and decision-making. Large language models and vision language models are bringing human-like reasoning to autonomous driving. Instead of purely numerical perception, these systems can understand and reason about driving scenes in natural language. GPT-style driving agents analyze driving situations and generate explanations for driving decisions, making the system more interpretable. Language MPC combines language understanding with model predictive control, translating high-level language commands into precise vehicle trajectories. DriveLM integrates visual perception with language reasoning, allowing the vehicle to answer questions about its environment like, "Why did you slow down?" with responses like, "A pedestrian is approaching the crosswalk from the right." This language-based reasoning helps bridge the gap between the statistical nature of neural networks and the logical reasoning humans use while driving. 3D occupancy prediction is transforming how autonomous vehicles understand their environment. Rather than detecting individual objects with bounding boxes, occupancy networks predict whether each voxel, or small volume element, in the 3D space around the vehicle is occupied or free. Tesla's occupancy network is the best-known production deployment of this idea, using surround camera inputs to build a dense 3D representation of the scene. This is particularly powerful because it can represent arbitrary shapes, not just predefined object categories. A fallen tree, an unusual piece of debris, or an oddly shaped vehicle are all captured naturally. Surround Oc extends this with improved multi-camera fusion techniques. TPV Former introduces a triperspective view representation that efficiently encodes 3D information from 3 orthogonal planes, significantly reducing computational cost while maintaining accuracy. Reinforcement learning offers a powerful framework for teaching autonomous vehicles to drive through trial and error in simulation. The agent observes the driving environment, takes actions like steering and braking, receives rewards for safe and efficient driving, and gradually improves its policy. The critical challenge is sim-to-real transfer. A policy trained in simulation must work in the real world despite differences in visual appearance, physics, and sensor characteristics. Domain randomization addresses this by randomly varying simulation parameters like lighting, weather, textures, and vehicle dynamics during training, forcing the agent to be robust to visual variations. Curriculum learning starts the agent with simple scenarios and progressively introduces more complex situations, similar to how a student driver progresses from empty parking lots to highway driving. Together, these techniques are closing the reality gap and making simulation-trained policies increasingly viable for real-world deployment. One of the biggest bottlenecks in autonomous driving development is data. Collecting, labeling, and curating real-world driving data is expensive and time-consuming. Generative AI is revolutionizing this by creating photorealistic synthetic driving data at scale. Diffusion models can synthesize realistic camera and LiDAR sensor data, generating rare scenarios like accidents or extreme weather that are difficult to capture in the real world. Neural radiance fields, or NeRF, can reconstruct 3D driving scenes from a sparse set of real images, allowing engineers to render the scene from any new viewpoint. 3D Gaussian splatting achieves similar scene reconstruction, but with real-time rendering speeds, making it practical for interactive simulation. These generative approaches dramatically reduce the cost of data collection, preserve privacy by creating synthetic rather than real-world imagery, and enable unlimited generation of rare and dangerous scenarios that are essential for safety validation. Let's recap the key takeaways from this chapter. First, robotaxi services from Waymo and Beidou are already scaling to hundreds of thousands of rides per week, proving commercial viability. Second, end-to-end AI systems are replacing traditional modular pipelines, simplifying the architecture while improving performance. Third, world models allow vehicles to predict and simulate future driving scenarios internally. Fourth, large language models are bringing interpretable reasoning capabilities to driving systems. And fifth, generative AI is solving the critical data bottleneck by synthesizing unlimited realistic training data. In Chapter 4, we'll explore the simulation and testing infrastructure that makes all of this possible, including digital twins, scenario generation frameworks, and the validation methodologies needed to certify autonomous vehicles for public roads.